Okay, let's discuss nested quantifiers. Let's take a look at a statement like this. Every real number has an additive inverse. First, to go any further, we need to discuss what an additive inverse is. Just to remind you, that's the idea that, hey, if x is 3, then we call y equal -3, it's additive inverse. In other words, if you take these two numbers and add them together, you get 0. So the statement we're dealing with here that we want to symbolize is every real number has an additive inverse. To begin, we're dealing with two numbers. We'll call them x and y because we're real creative like that. We'll say their domain is real numbers. That's, again, this fancy R. Well, how are we going to symbolize it? We say for all the x's. So any x, you pick that x. After you've chosen that x, I can go find the y that is its additive inverse. So when you add them, you get 0. Let's see this again. Every non-zero real number has a multiplicative inverse. The multiplicative inverse is similar. It's a statement that any two numbers are their multiplicative inverses if you can take them and multiply them to get 1. Again, this is a statement about real numbers, so we're going to say let the domain of x and the domain of y be all real numbers. There's a little bit of a trick here at the beginning. We're going to have to restrict the domain because we're saying for every non-zero real numbers. So for all the x's, which of course x is a real number, except x can't be 0, there is a y, which is also a real number, such that x times y equals 1. You can typically symbolize these statements a couple different ways. A lot of it has to do with your choice of the domain for your variables. Instead of restricting domain, we could just have a different domain for x. We'll dive more into set notation later in the course, but this symbol here is all real numbers, only we're removing 0. So we read this as the domain of x is all real numbers except 0. Let's try and symbolize the commutative law for addition. So this is the law that says we can reverse the order of addition. This one's pretty straightforward. You take any pair of real numbers for all x and all y. X plus y is the same as y plus x. So what we want to dive into then is the order of these quantifiers, because there is some significance about the order that we're going to put them in. So the first one we're going to look at here is when you have a case where it's all in all. Let P of xy denote x plus y equals y plus x with a domain all real numbers for both of them. This is the example we just saw. And what I want to discuss is it any difference if I say for all x and all y versus if I say for all y and all x? Notice that the inputs don't swap for my two propositional functions. They still go in the same order, x then y. Well, the first one says for all real numbers x, for all real numbers y, x plus y is the same as y plus x. Second one, for all real numbers y, for all real numbers x, x plus y is equal to y plus x. These expressions are saying the exact same thing. In fact, you can often read this as for all pairs of x, y. So the order for all x and all y can be switched. Makes no difference whatsoever. Let's consider the case where P of xy denotes x times y equals 1. Right, this is our with where x, the domain of x is all real numbers but 0, and the domain of y is all real numbers. This is our multiplicative inverse. Let's use this as a case study for all followed by the existential quantifier. Is there a difference between me saying for all x there exists a y versus saying there exists a y for all x? Let's take a look at both of these a little closer. For all x there exists a y says no matter which x you choose, I can go and find a y such that pxy is true, right? You pick an x, I will go find a y that is its multiplicative inverse. There exists a y for all x says there's a y that we can pick first, such that no matter what x you pick, it will be the multiplicative inverse. So this says that there's a number out there that is every number's multiplicative inverses. The one on the left is true. The one on the right is false. So just by looking at the truth value assessments here, we can see that these are not equivalent statements. So the order of the universal and existential quantifiers cannot be swapped. Finally, let's look at there exist and there exist. We're still looking at this multiplicative inverse example. Let's say there exists an x, there exists a y, pxy. There exists an x, there exists a y such that pxy. We could also say there exists a pair xy such that pxy. Alternatively, we could say there exists a y, there exists an x such that pxy. So whereas before for all x and all y said for every possible combination of xy, this says there is a pair xy that exists somewhere, at least one. So the order of exist and exist can be switched. This is summed up in a table that you will find in your notes. So let's see if we can translate the following mathematical statement. Just take it and put it into some symbols, symbolize it. The product of two negative integers is positive. Going to talk about, since we're talking about integers, two of them, I'm going to pick two different variables, x and y. I'm going to say their domains is a set of integers. This is represented by a double bold z. For all x and all y, if x is less than 0, so x is negative, and the y is less than 0, so if the x is negative and the y is negative, that implies that the product of multiplying them would be a positive number. Again, this is the way I would prefer to do it. You could also, quick way to do this is to restrict the domain. It makes the statement a lot easier. You could say, I'm sorry, change the domain to just be negative integers. The square of the sum of two real numbers is always non-negative. Take a second, see if you can figure this one. This is what I got. We're talking about two real numbers, so the domain of x and y is all real numbers. And we're saying that this is always going to be true for any two real numbers. So we say for all x, for all y, take them, add them, square it, you get a number that is greater than or equal to 0. Okay, let's take a look at a much more complicated one. This is a definition you're familiar with from calculus. The definition of the limit as x approaches a of f of x is equal to L. What all is this saying? What is the technical definition? You may have seen this in your calculus class. We're finally ready now to tackle this and symbolize it. It says that for every real number epsilon greater than 0, there exists a real number delta greater than 0 such that the distance between f of x and L is less than epsilon, as long as you're promising that x is within delta distance of a. So in this case, there are three variables to talk about: epsilon, delta, and x. All of them are real numbers. So let's take this one step at a time when we go to symbolize it. We're going to start with this statement that the absolute value of f of x minus L is less than epsilon when the absolute value of x minus a is between 0 and delta. Just rearrange this a little bit. This is why way back in the beginning of section 1.1, I was talking about making sure we get our logic and going in the proper direction. If you can promise that the x is within delta of L, that is that the absolute value of x minus a is less than delta but greater than 0, then we're supposed to guarantee for the limit to exist that f of x minus L in absolute terms is less than epsilon. This if-then statement translates nicely into an implication. And we're told that this needs to hold for all the x's. Well, that's a quantifier. So for all x, if the absolute value of x minus a is between 0 and delta, that would imply that the absolute value of f of x minus L is less than epsilon. So all that remains is to add quantifiers for epsilon and delta. For all the epsilons greater than 0, there exists a delta greater than 0, where for all the x's, we get the rest of the statement. Luckily, those two quantifiers come pretty directly from our definition at the top there. For every real number epsilon greater than 0, that's our quantifier for all epsilon greater than 0. There exists a real number delta greater than 0. There exists a delta greater than 0 quantified. You'll occasionally be asked to go the other direction. So here's a symbolized statement. What is this trying to convey to the reader? What is being stated here with the symbols? It can help to get used to just reading them straightforward. That's a little bit different than comprehending them, but just to read this off, this says there exists an x such that for all y, x plus y equals y. Take a second to assess the validity of this. This is true. If x is 0, x plus y equals y is then 0 plus y equals y, which is just y equal y, which is a true statement. Note that I keep putting the proposition there in parentheses. It gets really confusing if you try to run this on as an equation. That equal sign is the thing in question here. We'll see that show up later in the course as well. Take a second, pause the video, try to interpret this one, and then tell me if you think it's a true statement or not. Okay, for all x, for all y, if x is greater than or equal to 0 and y is less than 0, then x minus y is greater than 0. Even reading it aloud, it can be hard to figure out what this is trying to say to me. It turns out to be a true statement, but for me to understand it, I have to read it this way. For any positive or 0 number and any negative number, if you subtract the negative number from the positive or 0 number, you get a positive number. And that is because you are subtracting, right? This will be negative. So when you subtract it, it will be a positive number. So you're going to have something here that is 0 or positive. Sorry. And then when you subtract a negative number, it's the same as adding. So you're going to get a true statement. Let's try and take our English and put it into symbols. If we let C of xy denote x and y have chatted over the internet, let's take the statement and see if we can symbolize it. There are 2 students in your class who have not chatted with each other over the internet. 2 ways to do this. The first is to let the domain just be students in the class. And then we're saying, hey, there is a pair of students who have not chatted over the internet. So there exists an X, there exists a Y, where it is not the case, CXY. Just like with a lot of the other ones, we can do this differently. The symbology turns out a little bit differently depending on our domain. If we let U of X and U of Y be all people, we have to come up with a new function. You can always do this if you want. We're going to let H of X denote the idea that X is a student in your class. So now we need the following to be true. We need them to X to be in our class and Y to be in the class and them to have not chatted over the internet. There is a student in your class who has chatted with everyone in the class. Again, let's approach it the first way with the domain for both variables being all students in the class. We say there exists a student who for everyone, so there exists an X for all Y, CXY. They've chatted with everybody. We can do the same trick if we want to introduce a new propositional function. X is a student in your class, only now hits all those same 3 things. But X is in the class, Y is in the class, and they have chatted. Only our quantifiers are there exists a student for all the students. One final topic to discuss is negating these nested quantifiers. So say you're asked to negate there exists in x for all y, x plus y equal y. So on the first line here, I've just taken the statement and placed the negation symbol in front of it. This is the easy way to quote unquote negate it, but again, it's not the way to comprehend what it's saying. So what we're going to do is we're going to push this negation symbol inwards. What do you get when you negate exist in x? What's the opposite of there exist in x? Again, recalling that this statement is true, so the negation of it, we should end with something that's false. When you push that negation in one level from the exist x, it turns it into a for all x statement. So we push that negation symbol in just one level. We're going to push it in again. And now we have for all x there exists a y, where it's not the case that x plus y equal y. Well, push that negation symbol in just one more step farther, and we get the full negation of the statement. For all x, there exists a y, x plus y does not equal y. But that is a false statement. Let's again turn our attention to a much more challenging example. So we want to negate the following statement. For all x and all y, if x is negative and y is negative, and I multiply them together, I will get a positive number. So we want to negate this. So we place that negation symbol outside, and let's, for the way I term it, let's push that negation symbol in. We pushed it in the first level, we changed that all of x into there exists in x. We push it in again, now we've changed for all x, all y into there exists in x, there exists in y, where it's not the case. Boom, this big long propositional statement. And this is where it gets tricky. We don't have a way to negate the implication, at least not directly. So I'm going to use some color coding here, and I'm going to compact these down into propositions so you can see what I'm getting ready to do. So I'm taking x is less than 0 and y is less than 0, calling it p. I'm going to shade all that blue. Got my implication in red there, and I got my x times y greater than 0 as a q. And I'm going to use table 7.1. This is going to let me change this implication, right, because I can use the logical equivalency to turn it into a or statement. So I'm going to negate the blue part. I'm going to change the implication into an or symbol and leave the q alone. So this is what I get. Now I'm ready to push that negation in. To do that, you can think of this as distribution almost. I need to negate every part that's in here by De Morgan's. So you can see that I now have a double negation in front of the blue. My or swapped to an and I have a negation in front of the green part. Well, now double negation law kicks in, right? I have the white negate and the blue negate. They go away from the double negation law. And I push that negation into the green part. Instead of saying x times y is greater than 0, I can rephrase it as xy then. What's the negation of being positive? Well, you're 0 or negative. So this is the end negation statement. There exists an x, there exists a y, so there exists a pair x and y, where it is the case that x is negative and y is negative. When you multiply them, you get a 0 or negative number. That is clearly false.